Okay, so in the previous video, we saw this interesting phenomenon. If you take the family of excentral triangles to the family of three periodics in the elliptic billiard. So the elliptic billiard is shown as this upright ellipse here, and this is a sample three periodic, the dash blue, sample three periodic in the elliptic billiard. And the blue triangle, which passes through the vertices of the three periodics, and is perpendicular to the bisectors, therefore it's going to be tangent to the elliptic billiard itself. This solid blue triangle here is known as the excentral triangle, and the family of excentral triangles is a constellation family. What we were looking at in the previous video was if we actually took the three vertices of this excentral family, so let's turn off the three periodic, and we inverted those 3 points with respect to a circle centered at a given point Pn on the plane. And the result that we described in the previous, or the observation we described in the previous video, was that the Symmedian point x6 of this inversive family was stationary in the line connecting the common center to Pn. And recall that the original family maintains its Symmedian point x6 also stationary at the center. So to summarize the result in the previous video, this solid blue family here of acute excentral polygons, it begets a whole family of inversives, right? So I can place this inversion center anywhere in the plane, and any one of its offspring, inversive offspring, is going to be a family of triangles whose Symmedian point is also going to be stationary. So that's the result on the previous video. Let's place this guy a bit closer here, for example over here, so we can see this better. Let's scale in a bit. So you can see here that this family of inversive triangles, okay, has this Symmedian point stationary on the line connecting the stationary Symmedian of the excentrals with P-inv, our arbitrarily chosen center of inversion. Okay, now today I stumbled upon an interesting additional invariant here. Let's remove the scale. And this new invariant has to do with the concept of the cosine circle. Cosine circle of a triangle ABC. Okay, and you can look this up, and I'm going to leave a link in the description. You can look this up in Math World. But it is a circle of any triangle centered on its Symmedian point, x6, with radius given by a very simple expression. The product of the side lengths divided by the square, or the sum of the square side lengths. So if you have a triangle with side lengths ABC, the radius of this cosine circle is going to be something like ABC divided by A squared plus B squared plus C squared. Okay, so one result we've known for a while is that that ratio, ABC divided by the sum of the square side lengths, is conserved for this family, for this blue family here, the solid blue, the family of excentrals of three periodics. Therefore, if I were to draw its cosine circle, this red circle here, you're going to get a circle centered on x6 whose radius is also fixed. So you get this red circle, and we've derived that expression in terms of AB of the elliptic billiard. Okay, one thing that we do notice is that for different aspect ratios of the elliptic billiard, this inner brown ellipse, this cosine circle not only is it stationary, but it's always exterior. So I could play around with the aspect ratio of this upright elliptic billiard and notice that that red cosine circle is always exterior to the elliptic billiard itself. Let's bring the three periodics again. So three periodics are inscribed on this brown elliptic billiard, and the cosine circle of the excentrals is stationary. So it has both stationary center on x6 of the excentrals and invariant radius. Product of side lengths of the blue, solid blue, divided by sum of square side lengths of the solid blue. Very well. So this video is about investigating the cosine circle, not of the original family, but of the inversive family. So let's recall what this inversive family is. Let me scale in a bit more. This inversive family here, whose Symmedian point is also stationary and collinear with the original Symmedian and P-inv, this inversive family is obtained by inverting or performing inversions of the three excentral vertices i.e. the excenters of three periodics in the elliptic billiard. So these vertices are also known as the excenters. They're the vertices of the excentral triangle, right? So I'm performing three inversions. I'm taking each one of these points, okay, considering a unit circle centered on PMV, and I'm inverting these 3 points with respect to PMV, so I get these new magenta vertices, and I get this new family of quote-unquote inversive triangles. So the result in the previous video was that x6 of this family is stationary. Okay, well, I can also calculate what the radius. So I already know that whichever radius of the cosine circle is here, its center is stationary, because the cosine circle of this inversive will be centered on x6. It turns out its radius too is invariant. So if I take the side lengths and I take the product of the side lengths A, B, C inversive and divide by the sum of the squares of the side lengths, that ratio will also be invariant here. So let's draw that cosine circle. There it is. So it's the little red circle there. Let's scale it up so we can see it a bit better. This is the cosine circle of this triangle. As I animate the family, its radius is stationary. Okay, so if I move the position of the inversion center around, that radius, turns out it changes ever so slightly. It is not invariant over PMV, but it is invariant for a given choice of PMV, right? So scale this out so you guys can get a sense of, let's change that aspect ratio a bit. I'm going to turn off the cosine circle of the excentral because that's an older result. So here you see in dashed red the cosine circle centered on x6 star of this inversive family. As I move my circle around, or my inversion center around, my cosine circle moves around. So what we're saying here is actually very simple, that when you perform an inversion, such as we just described, okay, and let's take a better position of this triangle. There it is. Okay, and let's zoom in a bit. So when you perform this inversion of the excenters with respect to a circle centered anywhere, you get this new triangle, and what we're seeing here is that the product of side lengths divided by the sum of square side lengths for whichever choice of PMV is conserved. This implies that the radius of the cosine circle is also conserved. Doesn't matter where PMV is. I can place PMV, for example, in the center of my system, and you get this cosine circle. You can place it on a focus, for example this one. You get this cosine circle. There's probably interesting properties to their radii. We have to investigate those, and you can place it over here, but you can see that the radius is not constant. This is a smaller circle visually than that one over there. So compare that one with this one. This one's smaller, this one's bigger, but the radius of the cosine circle is actually conserved. So looks like it gets a little smaller as my PMV gets further and further from the center of the system, right? And it's probably maximized, I would guess, when I'm right at the center, but this is just visual. Alright, so this is a new observation about this intriguing system of triangles. See you in the next video.